back, folks. Jayland Bio here with another exciting video. Today we are going to focus on kinetic molecular theory and gas laws. Now, we've previously talked a lot about the different intermolecular forces that are present between solids, particularly ionic solids, metallic solids, covalent network solids, molecular solids, and how that has an impact on boiling point, freezing point, vapor pressure, etc. Well, today we're going to dive in and talk a little bit about how gases exhibit some of those properties and how all of the different variables of gases, pressure, temperature, volume, moles are all related to one another, and how we can do some mathematical calculations with that. It's going to be an exciting video. I know I'm pumped up. It's 5:30 in the morning. Let's go. Your learning objectives for today. Hopefully you will be able to calculate a variety of variables using the ideal gas law. You should also be able to evaluate gas mixtures, pressures of each component, and the laws of partial pressure. Identify the relationship between kinetic molecular theory and solids, liquids, and gases. And then also, lastly, differentiate between the ideal gas law and real gas behavior. Now, we explained the relationship between pressure, volume, moles, and temperature. We typically use the ideal gas law, and you should be very familiar with this. It is PV equals nRT, where P is pressure in either atmospheres, kPa, or millimeters of mercury. Volume is in liters, N is in moles, and temperature is in Kelvin, which is Celsius plus 273.15. The value of R differs based on what unit of pressure we're looking at. So it's 0.0821 when the pressure is in ATM, 8.31 the pressure is in kPa, 62.4 when the pressure is in millimeters of mercury, etc. So think about what relationships exist between variables. If we isolate N by itself, you get PV over N times T. So you should be able to think about some of those relationships. For example, if pressure increases and the volume and number of moles stays the same, what happens to the temperature? Well, it increases as well. They are directly proportional. Pressure and volume. If the pressure increases, the volume decreases. So you should be able to establish some relationships with these. If they multiply, so for example, if you set it equal to N, like I said, you get PV over N times T. If the two variables multiply, they are inversely proportional, meaning that as one goes up, the other goes down. If you would divide those two variables, they are directly proportional. So as one goes up, so does the other. So as pressure goes up, so does temperature, etc. Now keep in mind that the ideal gas law does not explain the actual behavior of real gases. There are derivations or deviations that result from the fact that small intermolecular forces are still present in gases. You can see that in the van der Waals equation for real gases on the left, that there is correction for attractive forces which impacts the pressure. We also need to consider the fact that the particles actually take up space themselves. Usually when we deal with volume, it's just the volume of the container. Well, the particles themselves actually contain volume. So we need to take corrective measure for that. So understand that the ideal gas law is okay for what we need it for. But in real circumstances, there's actually quite a lot of difference between an ideal gas and a real gas. Notice the chart on the right. P times V, that line going straight across. If we look at real gas scenarios, you can see the different products you get when you multiply P times V. Furthermore, take a look at the one that's closest to the top. It is CO. CO is polar, whereas CH4, H2, and HE are decreasing in polar character, increasing in nonpolar character. So what this tells us is that polar molecules tend to deviate more from the ideal gas law than perhaps nonpolar molecules. Now, in a mixture of gases, the pressures exerted by each component is independent of the other components of the gas. So what you would have to do is you would take the total pressure that is present and you would need to multiply that by the mole fraction. Once you get that, then you get the pressure that is exerted by that specific gas. Again, mole fraction is what's critical here, because remember, a mole of any gas is 22.4 liters. So when you have a mole of gas, it's going to apply the same amount of pressure as a mole of any other gas because it's the same number of molecules in an ideal situation. So we need the mole fraction, we need the total pressure or the partial pressure. Again, any two out of these three variables and you should be able to solve for the others. There will be some practice questions on this on your homework, so make sure that you are aware of this. And then as a result, the total pressure of the gas is directly related to the partial pressures of each individual gas. So if I have containers A, B, and C with 100, 250, and 200 kPa respectively, the total pressure, if all of those gases are in the container, are going to be 550 kPa, because the partial pressures add up to equal the total pressure of the gas inside of the container. A lot going on here, but some key concepts to understand. The concepts of kinetic molecular theory describe the motion of a gas. Okay, now some of these focus on ideal gas law principles. Some of them are pretty realistic. The volume occupied by the individual particles of gas is negligible compared to the volume of the gas itself. So that's basically saying we don't take into consideration the volume of the particles, even though in a real gas situation we probably should. The particles of an ideal gas exert no attractive forces on each other and their surroundings. Again, ideal gas law. Gas particles are in a constant state of random motion and move in straight lines until they collide with another body. The collisions are completely elastic, meaning that total kinetic energy is observed, which is not necessarily true. And the average kinetic energy of the gas molecules is directly proportional to absolute temperature only. When we say absolute temperature, we're referring to the Kelvin scale. This implies that molecular motion ceases or stops if the temperature is reduced to absolute zero. If you've taken physics, you're probably aware that Ke equals 1/2 m times v, where m is the mass, v is the volume, and Ke is representative of kinetic energy. If there is no velocity, then there is no kinetic energy. So you should be able to utilize these concepts in a pretty straightforward manner to be able to solve any of the problems that you'll see here in the third part of Unit 3. Thanks for listening. Have a great day, guys, and we will talk to you later. Bye-bye.